The last section of Chapter 9 is called Taylor and Maclaurin series, and I think you're really going to like this. All of the mathy people who aren't used to all of this upper level math that we've been doing really like the Taylor and Maclaurin series because it's kind of like a puzzle and it just requires us to find a pattern. And it's a pretty straightforward algorithm for doing all of that. Essentially, the hardest part of the Taylor and Maclaurin series is to find all of the derivatives. So if your derivative game is not strong, you'll either really struggle with this or your derivative game will get much stronger. So essentially what we're going to do is we're going to find the first derivative, the second derivative, the third derivative, and so on, to find all of the values that create the sequence. And we're going to use that to come up with a pattern so that we can then write it as a series. So we're going to write it as a summation as we have been doing, but this is sort of going backwards. So we're going to use the values that we come up with to find the pattern to come up with the series. So let's do our first example together. And when we're dealing with the Taylor series or Maclaurin series, which is technically what we have when we have c is equal to 0. We're going to start by writing down the function, the first derivative of the function, the second derivative of the function, the third derivative of the function, and then evaluating each of those at the center. So this is technically like the 0th derivative. So the first function is just what's given to us, which is e to the negative 4x. So that is not the derivative, that's the original function. The first derivative of the function is using the chain rule, which would be e to the negative 4x, then the derivative of negative 4x, which is negative 4. Continuing that strategy, I would take that expression times negative 4, which would make it positive 16 e to the negative 4x, and that expression times negative 4, which gives me negative 64 e to the negative 4x. I'm then going to evaluate each of those at 0, because that is the center. So now I'm going to find f of 0 at 0, the first derivative at 0, the second derivative at 0, and the third derivative at 0. So that would give me e for my first one. This is obviously e to the negative 4 times 0, which is e to the 0, which is 1. And then using that same strategy, this is going to be 1, but times negative 4, so this is negative 4, this is 16, this is negative 64. Now what I'm going to do from here is start to write out my series. So e to the negative 4x, I can write it using this format. So this in the numerator is exactly what I've just found here, and that's why I wrote it in this way with 1 and 2 and 3 instead of 1 dash and 2 dashes and 3 dashes. So my numerator for my first value, where n is equal to 0, would be 1 over 0 factorial, and then x minus c, now c is 0, so that's just x, to the nth power. For n equal to 1, I'm going to now use negative 4, and then 1 factorial x to the first. And then for f, the second derivative, it's 16, and then 2 factorial, because n is 2, x squared, and then negative 64, 3 factorial x cubed. Now what I'm trying to do is I want to write it as a summation. So I just want to simplify the pattern that I'm finding. So let's just do a little bit of simplification. E to the negative 4x. My first value is 1 over 0 factorial x to the 0. My second value is now minus 4 over 1 factorial x My third value is 16, which I'm going to write as 4 squared over 2 factorial x squared. And my third value is negative 64, so I'm subtracting. Actually, let's go ahead and leave the negatives on there. So plus negative 64, and 64 is 4 to the third, 3 factorial x cubed, and of course this continues forever. Now, why did I want to write it in that way? Because I want to be able to write this as an infinite series. So the summation is, as n goes from 0 to infinity of what? So let's just take a look at what's happening. This value is positive, this value is negative, this value is positive, this value is negative. And so I know that's just an alternating series. So it's either going to be negative 1 to the n or negative 1 to the n plus 1. Since my first value is positive, it's negative 1 to the n. That makes all of the even values positive. Then what do I have? I have 4 to the first, x to the first, 4 squared, x squared, 4 to the third, x to the third. So that means I'm going to write 4x to the nth, because remember this was n1, n2, n3, and so forth. And then in my denominator I have 1 factorial, 2 factorial, 3 factorial, so that's just n factorial. So I have now successfully written e to the negative 4x as a power series or a Taylor series. All right, let's try another example using the Taylor series. Again, this one is not going to be centered at 0, so it is a true Taylor series, but we're going to go about this in the same way we did before. I'm going to use my original function, which is 1 over 1 minus x. And again, if they didn't specifically ask me to use the Taylor series, I would probably not. I would probably use the strategy we learned previously using the geometric series, because this would work very well with that. But we'll go ahead and use this because they've asked us to. I'm going to rewrite that function as 1 minus x to the negative first. So the derivative function, the first derivative, would be using the power rule, negative 1, 1 minus x to the negative 2, and then the derivative, the chain rule says now take the derivative of 1 minus x, which is negative 1. So that turns into positive 1, 1 minus x to the negative 2. Then the second derivative, using that same strategy, would be negative 2, 1 minus x to the negative 3 times negative 1, or positive 2, and then 1 minus x to the negative 3. And then the third derivative would again be using negative 6, 1 minus x to the negative 4th times negative 1, or positive 6, 1 minus x to the negative 4th. Now, if I'm going to find each of those values at 2, for the first value would be 1 minus 2, so negative 1 to the negative first, or 1 over negative 1 to the first, which is negative 1. The first derivative at 2 would be 1 over negative 1 squared, which would be 1 over positive 1, or 1. The second derivative at 2 would be 2 over negative 1 to the third, which is 2 divided by negative 1, or negative 2. And the third derivative at 2 would be positive 6 over negative 1 to the fourth, which gives me positive 6. Now let's use all of those values to rewrite 1 over 1 minus x using our definition. So I'm going to start with these coefficients, that's my numerators, that's why I had to find them, over n factorial, and then x minus c to the nth. So the first guy is negative 1 over 0 factorial, because the first guy is when n is 0, of x minus c, so x minus 2, to the nth power, and n is 0. And then the next one is 1 over 1 factorial, because n is 1, and then x minus 2 to the first, and then I have negative 2 over 2 factorial, and this is x minus 2 to the second, and then I have positive 6 over 3 factorial, and then x minus 2 to the third, and this pattern would continue. So I'm going to get these out of the way just because I don't have room for that. But keep in mind that that's where what we're doing is n is 0, n is 1, n is 2, n is 3, and the pattern continues. So I just need to think about how could I rewrite this? What do these values equal? So sometimes it's better to go ahead and evaluate this. So the first guy is negative 1 over 0 factorial, which is 1. So this guy is negative 1, and then x minus 2 to the 0. And this one is positive 1, 1 over 1 factorial, which is 1, and then x minus 2 to the first. And this is negative 2 over 2 factorial is 2 times 1, which is 2. So negative 2 over 2, which is negative 1. And then x minus 2 squared. And then the next one is 3 factorial, 3 times 2 times 1, which is 6. So that's 6 over 6, or 1, x minus 2 to the third. So I can see the pattern now is that the coefficient is negative 1 and positive 1 alternating. And so because my first guy is negative, I can write 1 over 1 minus x as negative 1 to the, I'm sorry, I need to write the summation first. I'm getting ahead of myself. The summation as n goes from 0 to infinity of negative 1 to the, not n, because if I used n, then the first value would end up being positive. So this is n plus 1 times x minus 2 to the n. And that should give me the correct value. And again, you can always just do a test to see if it works. So especially if you're dealing with the negative 1 and making sure that you have the correct sign. If I plugged in 0, that would give me negative 1 to the 0 plus 1, which is to the first, and then x minus 2 to the 0. Does that give me the correct value here? Yes, it does. So I'm convinced, and we'll just go with that. Here is my final solution. Let's do just one more example, and in this example I want to use a trigonometric function because we haven't dealt with those in a while, and you should always be dealing with trigonometric functions. So we'll start with the original function, which is of course sine of x, the first derivative, which is cosine of x, the derivative of sine is cosine, the second derivative, which is negative sine of x, the third derivative, which is still using that negative, so negative cosine of x, and then the fourth derivative would be the derivative of cosine, which is negative sine, but now it's negative negative sine, so it's positive sine. So as I can see, this guy would be the fourth derivative, and the fifth derivative, and the sixth derivative, and so on. So this is f6 and f7 and continuing forever. So now let's evaluate those functions at 0. If I take the function of sine of 0, I'm going to get 0. And if I take cosine of 0, I'm going to get 1. And negative sine of 0, I get 0. And negative sine of 0, I get negative 1. And that pattern would continue and continue and continue and continue. So just as we have in our last examples, I can say f of x, or sine of x, is equal to 0, and then again c is 0, so it would be 0 over 0 factorial, and then x to the 0. And then I would have 1 over 1 factorial x to the first, and 0 over 2 factorial x squared, and negative 1 over 3 factorial x cubed, and then the coefficients would continue to alternate. 0, 4 factorial x to the fourth, positive 1 x factorial, I'm sorry, 5 factorial x to the fifth, 0, 6 factorial x to the sixth, negative 1, 7 factorial x to the seventh, and so on. And you might be thinking, well, geez, we don't usually do that many terms, but the reason I did so many is because this guy is obviously a 0, and this is a 0, and this is a 0, and this is a 0, so every other term is canceling out. So I now have sine of x is equal to 1 over 1 factorial, which is just 1, x to the first. So my first one is 1x. My next term is negative 1 over 3 factorial, so it's negative 1 x to the third over 3 factorial, and then positive 1 x to the fifth over 5 factorial, and negative 1 x to the seventh over 7 factorial, and so on. That's why I did so many, because all of those zeros canceled out, and I needed enough left over to come up with a pattern. So now what I need to think about is the fact that this is when n is 0, and this is when, this is when n is 1, and this is when n is 3, and this is when n is 5, and this is when n is 7. And so I need the even ones to essentially go away, and I need the odd value, so I need, really what I want to do is rewrite my function. So let's do sine of x. I want to rewrite it so that when n is 0, I get this value. And when n is 1, I get this value. So how am I going to make this work? I really just want the odd values. So I'm going to essentially look at the fact that 1 and 1 factorial, 3 factorial, 5 factorial, 7 factorial, this is just an arithmetic sequence. An arithmetic sequence has the first value of 1, and it goes up by the common difference. So that's 1 plus 2n. So if I can keep that in mind, then I know that not only the exponent, but also the factorial on the bottom are using that same arithmetic sequence. So I get x to the 2n plus 1, which is the same as 1 plus 2n, divided by 2n plus 1 factorial. So let's talk about the negative part in just a moment, because obviously this is an alternating sequence, negative, positive. But so far, let's see if I'm on the right track. If I chose n is 0, that would give me x to the 2 times 0 plus 1, so x to the first, and then 2 times 0 plus 1, 1 factorial. That gives me my first value. Let's look at my second value. My second value should be negative, and we'll deal with the negative in a minute, x to the third over 3 factorial. So that means if I plug in 1, x to the 2 times 1 plus 1 is 3, over 2 times 1 plus 1 is 3 factorial. So this part is spot on, and now we just have to look at the alternating negative. So it's going to be a negative 1, and then you have to decide, is that to the nth or the n plus 1? Now, because my first value is positive, I want all of the even values to be positive, or every other starting with positive, and all of the odd to be negative, and so that's going to give me -1, oops, not to the 0, -1 to the n. So this is my final solution, is the summation as n goes from 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Coming up next, let's take a look at the binomial series.